I am Aves and I am going to teach you how to get to Mars, and my fellows Zain and Fahad are going to assist me to cover this topic. We know that Mars is the fourth planet from the Sun and second smallest planet in the solar system, also known as red planet. The distance of Earth from the Sun is 93 million miles. On the other hand, the distance of Mars from the Sun is 141 million miles. The diameter of Mars is 4,220 miles, while the Earth's diameter is 7,926 miles. The Earth's orbiting speed around the Sun is 18.5 miles per second, while Mars orbits around the Sun with a speed of 14.5 miles per second. The Earth takes 365 days to orbit around the Sun, while the Mars takes 687 days to orbit around the Sun. In every 2 years or so, Mars and Earth reach their closest point, that is known as opposition, when Mars can be as close as 50 million miles from the Earth.
Now the question arises that how long does it take for these two planets to align in a straight line? Keeping in mind that the Earth takes 365 days to complete its one revolution, while Mars concludes its one revolution around the Sun in 687 days. And doing some quick maths, we can see that it takes around 779 days to happen. That is, opposition occurs after every 26 months. Interesting, right? Though it seems that for a probe to travel in a straight line is the shortest way to reach the red planet, but the rocket science is not as easy as it seems. Traveling in a straight path requires high speed, which means more fuel, making the mission uneconomical. In addition, Mars is orbiting around the Sun, and the red planet would be long gone if the probe tries to reach its surface by traveling in a straight line. So, how should the spacecraft enter Mars? How can we travel efficiently? Well, the answer lies in the position of Mars when the probe will reach the red planet. There are two fundamental approaches: orbital transfer and Hohmann transfer. In coplanar transfer orbit, we launch the probe in an elliptical path which intersects both the circular orbits, that is, inner and outer orbits. In this approach, the spacecraft requires two impulsive burns, which means more fuel but less transfer time.
In a non-Hohmann or general coplanar transfer, the transfer ellipse intersects the two orbits at points other than its periapsis or apoapsis. Suppose at point 1 the spacecraft fires its engines to get into the transfer trajectory towards its destination orbit, and at point 2 on the transfer ellipse it fires its engines once again to get into the desired orbit. At point 1, delta V1 is the difference between the initial circular orbital velocity Vc1 and the orbital velocity at point 1 of the transfer ellipse. At point 2, delta V2 is the difference between the final circular orbital velocity Vc2 and the orbital velocity at point 2 of the transfer ellipse. We can calculate the total change in velocity required by the spacecraft by adding these two delta V's. Spacecraft also has to adjust its flight path angle to get into the transfer ellipse trajectory, which means that the spacecraft not only has to change the velocity magnitude but also its direction. Using the law of cosines, delta V1 can be expressed as follows. In a similar manner, we can compute the velocity change at point 2. Now suppose this is the orbit of Earth around the Sun. We want to achieve a higher orbit to get onto Mars by using minimum energy. Hohmann transfer is the minimum energy transfer, that is, we need minimum amount of delta V to get into a higher orbit. Here is my spacecraft, and the first thing I need to do is to fire rocket engines to get a change in velocity to achieve a new elliptical orbit. We fire the rocket engines at periapsis for a brief period of time and it goes all the way up to apoapsis of the transfer orbit. Now if we don't do anything, it will keep on moving in the transfer ellipse. So what we do is, when the spacecraft reaches apoapsis, we fire our rocket motors once again to circularize the orbit at the desired altitude. Once we do that, our engines cut off and we coast and remain in our new circular orbit around the Mars. As I said earlier, Hohmann transfer is the least energy transfer, but it also takes most time to get from Earth to Mars.